Hello everyone, welcome to the fourth lecture of week 11. So we have been talking about long sequence modeling, and this lecture will discuss further ideas in the same direction. We will talk about long sequence modeling problem in general, and we will focus on various aspects on modeling long sequence, including linear attention, how do you do fixed size KV cache, and we will talk about some memory based models for uh, particularly solving this particular problem. So, what is the long sequence modeling issue, the problem? So, in general, if you look back at the language modeling problem, what do you have? You want to model probability of y given x, right? So, x is the context that you have, and y is the text that you want to generate. Yes. Now, when you say long sequence modeling problems, so they would typically fall under three main categories, right? We will deal with them together. So, one is that you have a very long context and you want to generate, right? The generation may be short in itself. So, x is a long sequence and y may not be long. So, like you want to generate a short summary for a very long text. You have a very long document, you want to generate a summary for that. So, here x is very long. Or you may have a long text generation problem, like where y is a long sequence. Like somebody gives a prompt to generate a long story, right, based on a very few keywords as input. So, x is short and y is long. Or you may have both x and y as long, right. So, for example, you want to translate a very long document from Chinese to English. So, your input is also long and output both x and y are long, right, and that is where we would have to deal with many issues, like when you are doing generation, long generation, right. So, we talked about this KV cache, we have to maintain this KV cache for efficiency, but if you are doing a very long generation, the size of this KV cache increases, right. So, what is the effective way in which I can maintain the KV cache? So, what do I do with KV cache? How do I reduce the size of the KV cache? And how do I actually look back at a very long context? And can I look something beyond whatever is the input, right? So, that is where we will talk about the memory part. Now, there are two directions. So, one is that we can have some nice training methods, model architectures to learn self-attention models from long sequence data, or we can adapt the pre-trained LLMs to handle long sequences with no fine tuning effort. So, we will have both kind of methods. Somewhere we will change the architecture itself, right, and somewhere we will have some nice ideas in which the previously trained LLMs can handle long sequences. Now, the one we talked about in the previous lecture about using rotatory position embedding and position interpolation or ABF, it will fall under this category particularly, because I am not doing any fine tuning, I am just using the same model, but having some simple way in which I can extend it to handle long sequences. But we will see some more kind of architectures and ideas in this lecture. So, the simplest way in which I can extend is okay without because see what happens if you increase the length, you still have to worry about this order n square thing, right, in your computation self attention. That is also the how much memory you are storing and how to reduce this order n square computation. So, one very simple idea that we have already discussed, like in the previous lectures week 5, is that I can do in sparse attention. So, this is a standard self attention, my query is attending to all the previous keys and values, right. So, query I is attending over all the previous keys and values. In the sparse attention, what I can do, I can say okay, I can only attend to a subset of these, and we had various ways of defining these subsets. You can be based on blocks, you can have some global attention, some local attention, right. So, you may have only a set of indices for each I that are non-zero, right, others you can put at 0. So, it becomes a sparse attention, right, and you normalize your this softmax values only for this G, whichever are non-zero indices, right. So, you will compute your attention over these. So, that is the sparse attention, and we already talked about various methods for this. Sliding window attention, for example, is one very popular method. But what we will talk about today are some more interesting ideas. So, for example, one can say fine, So, I can use sparse attention and I can reduce the computation, but I will still have to store all the KV cache. Like if I have to do global attention, right, or I have to do some block-wise attention, I will still have to store some finite differences from that word. So, that means entire KV cache has to be stored during its inference, and that may be very inefficient, very much memory intensive, right. If I have to store the entire KV cache for, like, if I have to generate 30,000 words and have to store all the KV cache for all the layers, right. So, it will be a lot of memory requirements, and so especially if the sequence is very long, this becomes highly memory intensive. So, can we have some different kind of attention model where the KV cache is not explicitly stored, right. So, that is why we will talk about one particular idea called linear attention, right. So, the idea is that, okay, so if you can see from the equation that we will discuss in detail. So, what we will do effectively, I will store a summary of KV cache, like this mu I and vi are like effective summaries of these, some summaries that I will store. They are not exactly key and value summary, we will see what are these, and when a new query comes, I use these effective values that I have stored already to compute the score, right, and that is all the final attention output. So, I will not actually do compute over everything dot product into attention, I will not do that. I will just store a summary and use that to do my final self attention output, and this will happen in linear time, right, compared to the quadratic time that I was doing for self attention. So, what is the idea? Let us look at that in detail. So, what is the formulation of linear attention? This came in this paper, Transformers or RNNs paper, and this actually comes out very similar to RNNs, right. So, what is the idea? So, they say, okay, so let us focus on our original equation for this self attention output. This is my self attention output. What I do? I say, okay, for the ith word, I will take the query from ith word and key from any jth word, and for and let us use a general formulation for similarities. Let us say I took a similarity of qi with kj, right, and based on the similarity I multiply with vj. That is what I do. Similarity qi kj, multiply that with vj, right. If kj is more similar, I will use a larger chunk of the value of j and divide it by overall similarity of qi kj, right. So, that will be my weighted average of values, right. So, that is a generalized equation, right. So, where it uses a general similarity function. We talked about one similarity function, but this is a more general function. Now, its complexity is order n square, because you have to compute qi and kj, right, for all pairs, right. Now, so they say, okay, let us now try a kernel based formulation. So, when we say qi, so I will model it through a kernel, say phi qi, and similarly k phi kj, right. So, I will model both query and key through some kernels, right, and they have used a very simple kernel like exponential linear unit plus 1. So, what will happen now? I have this formulation. So, fine, I will write this like this. So, this is the kernel that I will multiply, kernel of qi transpose times q kj, and this is the denominator. Now, because of this matrix product being associative, so you can say, okay, this is common, I will keep it outside, and this is summation over j from 1 to n q k j v j transpose, and this will be again phi qi transpose will come outside, and the summation over j is equal to 1 to n phi kj, right. And now, by doing this simple kernel trick, this can be computed in linear time, right, for all the words. Now, how do you compute it in linear time for all the words in the sequence? So, they say, okay, so now let us look at it like this. So, I have one term phi kj vj transpose j is equal to 1 to n summation. So, let us call it Si. So, up to ith term j is equal to 1 to I phi kj vj transpose, right. Similarly, for this up to I term, I call it gi. So, Si and gi, two terms. Now, in terms of Si and gi, so if I store Si and gi for a ith point, what will be the effective self attention output for the ith term? I will say, okay, I will take the query, do the kernel multiplication, right, phi qi transpose multiply with Si divided phi qi transpose gi. This is constant time operation, right. So, once you have the query, does not require much computation, right. So, because Si and gi are already stored, phi is also a simple function. Now, but because you are storing this Si and Gi, you can just update them every time. So, if you go to I plus 1, so if you go to I plus 1, you will simply say, okay, this is the value, and I'll just add phi k I plus 1 v I plus 1 transpose. I'll add Si plus this. So, again in constant time I'll get Si plus 1, same with Gi to Gi plus 1, and I get that and I compute vi plus 1 prime. So these can be computed from the previous values in constant time, and that means I just have a linear complexity of computing the self attention for the entire sequence, self attention output for the entire sequence. Right? It goes down from order n square to order n, and that was the paper for linear attention. That so you don't have to store this kV for every token. I just have a trick by which I can store this Si and Gi, right, up to that point. It's like what we used to do in RNN. So we used to compute hidden state up to that point and use that to do everything else, right, next point of time. So this is very similar to that. And what they showed in their paper, that this is the paper Reformers. So this is the paper linear attention. They also compared with another paper Reformer. So this is the 3 things for Reformer. This is the original softmax based attention in the red curve, which is, you can see it's quadratic in nature, and this is the best among all, their linear attention, which in terms of both memory and time, right, it's very much efficient, right. So softmax scales with the square of the sequence length, while it is completely linear. So this is one particular direction you can do linear attention using the ideas of RNNs. Okay. Now let's go to another direction about the cache, right. So we talked about one way that you can do linear attention. That's how you can summarize the cache. Now, see, when you do this inference for the large language models, you have to store the entire left context so that you can make prediction for the future tokens, and that's why we use the KV cache, right. So all the keys and values you are storing. So, and this cost of caching, this keeps on growing as the inference proceeds. You need more and more memory for the caching. So typically what you do is, so you have this query, this memory has all the previous keys and values up to that point, and given this query I, you will attend over all of these. Right? This memory is simply the KV cache, the complete key and values up to now. Now we can even optimize this cache by different approaches, say sparse attention, linear attention, that we already talked about. Right? So another idea is that can we explicitly encode the context via an additional memory model. Right? So we'll talk about actually both in the context of KV cache, that how do you optimize them through sparse attention, and can we also encode some context, some additional memory, right, as an additional memory. So let's talk about the fixed size cache. Now this is easy. So let's say I have I may have a very long sequence, right, that I am trying to make use of. This is my KV cache. So in fixed size cache, I'll say I'll define a window. Say here my NC is my window size. So that means I'll store from I minus NC plus 1 up to I. So I'll store only NC different keys and values, and I'll only put attention over these and compute the output. So this is like a fixed window attention. So where I'm putting a fixed window cache, on which I can attend, right. So this is okay when you do not have any other alternative. I mean, you will not be able to make use of these words at all, right. So this is what you have a fixed. It's like a sliding window. And next time you go to I plus 1, again you will remove these and cache something new, right. So this is what happens. So first in, first out sort of scenario. Okay. Even there you can do other optimization. They're saying that okay, even on a fixed window, I may not store cache for the entire window, but I can do even a moving average, right. So I can say okay, I have these 4 things, so I'll just compute a moving average. And you know, you have a moving average. If you get a new value, you can still compute the moving average, right. You multiply it by 4 and this whole thing by 4, get the new thing, divide by, and minus this and divide by 4 again. So you get a moving average, keep on getting the moving average. So I can just keep in moving average, and this can be as simple as just an unweighted average, where I am having the keys for some previous window divided by the length of the window. same for values divided by the length of the window. It's the average value, unweighted. Or you can give a weight where you give more focus to the recent, the more recent context, right. So, you can say okay, I will have some weights for each position. So, you have NC position, I will have a separate weight for each position. So, you have some additional things betas, right, which can again be learnable, or you can simply use some function that is like increasing. So, beta 1 has a smaller value than beta 2 up to beta NC, right. So, you give more focus on the recent values than on the past values. And the good thing about it is that you do not even have to say remain fixed to a particular window. You can say okay, I will take it to a very large window, right, because you are not storing the entire thing, you are just storing a summary, right. So, storage is very limited, just 1 cross 2, right. So, only one key value is what you are storing. So, you can actually increase your context length here, then you can experiment with that, right, and you can actually store very small KV cache while making use of a lot of information, like you can use a lot of information while store very small, right. Now, in general one can say fine, if you are anyway doing that, I can use the entire KV cache and I can say this is my current information, and plus I add the current, the ith step divided by I plus 1, right. I can do an average over all the information till now, or I can have a neural network that say okay, this is my previous KV cache, this is my previous KV cache. So, this is the previous KV cache, this is the current value, now update them. So, this looks like a recurrent network. So, this is like a recurrent network. So, my previous memory, my new KV, and give me the updated value, right. This can be a neural network to update it. So, it is like a recurrent neural network such cache. So, these are the very I mean simple ideas, but this can be very effective when you want to do optimization in terms of your KV cache. Okay. So, and there are also methods that say okay, you can do a hybrid sort of cache. So, what is the idea? You say okay, so in the previous method the problem is that you do not have any token on which you can directly attend, you just have a summary on which you can attend. But suppose I want to directly attend to some tokens, at least to certain window I should be able to do that. So, the hybrid cache says okay fine, you can define two windows, one is a local window. So, you can have a local memory, say that is always sliding window, you can say I will take up to NC tokens I want to attend directly. So, you maintain a local window size say 4 cross 2, and you can have a compressed memory. So, everything before that you compress it by some method, it can be as small as 1 cross 2, or you may have other method for compressing, right. And as you keep on going further, what will happen? This will go in first in first out method memory. So, this will go out and you will get a new thing, right, in, and whatever will go out from here will go inside the compressed cache, right. So, this will go in the compressed cache. So, you will have normal KV cache and you will have a compressed cache. This is the local memory, this is the compressed memory. So, you can combine the two ideas in the hybrid cache, right. So, this is another idea, right. Now, finally, let us talk about the memory based methods. So, till now what we talked about, so where the memories we discussed till now, they are updating the KV cache, right, and this is the internal memories, because KV cache is what you have generated during your current sequence processing. But what if I want to, this is all internal to my processing, but what if I want to attend to some external memories, right. So, can I also do that? So, can I also attend to some large memories outside whatever I can hold, right. So, this can operate as an independent models to access large scale context for LLM. So, think about you are processing very long documents, right. Not everything is what you are not processing every token in the document, but you still want to attend to these large context somehow, right. So, how you can do that? So, we will talk about some methods. One very simple method, an interesting method is k nearest neighbor method, right. So, what you can do, so let us say you have this entire data set and this is the context for you to predict the next tokens, right. So, you want to retrieve the closest context in while you are generating this current word, rather than just a prefix that you can store in your memory, right. So, rather than going for internal memory, you want to make use of some external memory also. So, how we will do this? So, this is the paper that I am talking about, memorizing transformers on KNN lookup. So what is the idea that say, okay, I have a very long context. So now one idea we learned is that I can do a summarization of this long context, right, and do this KV summarization and using RNN or moving average. But what happens there? I don't have a direct access to all this context. I just have a summary. So in KNN lookup, I will not do any averaging or summarization of tokens at long distances, but I will retrieve the exact value of some tokens, right? Some exact tokens that I want to make use of, even from very distant context. And what they showed in the paper, that even if they have a sequence length of 1,000 to 62,000 tokens, they are able to do this lookup on a single TPU device, right, in a very reasonable step time. So this is like perplexity that they showed. This is on a adding a memory of 8,000 tokens. It improves perplexity drastically. This is the normal transformer. This is the memorizing transformer. Across all model sizes, you increase the perplexity, because now you are able to attend to much larger context, and this does not even take too much, I mean, computational time. It will take more time, but this is not like linearly proportional to the context that you are adding. So how do they actually add this? So this is the architecture that they had, right. So if you look at the architecture, like this is the mainly like a decoder, and you have the embedding layer and attention feed forward layer, and you have mode layer. So everything is like the normal decoder, right. This is what changes is this. So near the top of the stack, nearly the last layer of the transformer, you have a KNN augmented attention layer, right. So what it does its normal function like a normal attention layer. So it uses standard dense self attention on the local context and the input subsequence. So it will actually take the input subsequence to the self attention, but it also does something new that no other layer does. So they don't do this, only one layer does it. So that's why they are able to save time. They are not doing it at every layer. So what they will do here? So they will do a k nearest label lookup. So you have an external memory which have the cached key value pairs, the exact pairs, right? No summary, and you will do an attention, find out what are the k nearest neighbors to this, and you will use them. So it does an approximate k nearest neighbor search into the external memory and uses that, and whatever attention is computing, they will again be added to this external memory, right. So that means this key value are not coming through some separate distribution, they are from the same distribution, right. These values itself are getting added, but now you are able to make use of the long context by putting in the external memory, while the actual sequence may be very small, maybe say 512 tokens is what you can process, but you have an external memory to which only one layer can attend, that also by taking k nearest neighbors. So what they will do, so they have the same query. So the same query will be used for both the local context attention, and also for attending to the external memory, right. And the keys and values, they belong to the same distribution, because after each training step, the key value pairs in the local context will be appended at the end of the external memory. Now, I mean, is the external memory infinite? So they have a size, I mean, much larger size. So they have some, say, memory size, and of course, when it goes beyond this memory size, they will empty this. I mean, they will drop some key value paper, the oldest ones, to make it room for the new ones, right. So that they will do, but this M is typically much larger than what you can fit in a single sequence. As we saw, this can be some like 262K, 131K, huge, and they are able to do that because they do it only for single layer, right. They are not attending at every layer of the decoder. Okay, so what will happen in KNN lookup? So you have the query. Based on the query, you will do a lookup over this KNN, and you will get the top k key value pairs. For each query, you will get separate top k key value pairs. And now you have top k key value pairs based on the similarity. You will do normal attention, like so. You will construct an attention matrix, dot product of the query with all these key value pairs, and you will get a weighted sum of the retrieved values, right. Values are there. So by doing query key similarity dot product, and you will have the values, average score of the values. Okay, and you have the attention score over the local context also. So let's say VC is the output for the local context, self attention output, and VM is for the from the memory. Now, how to combine them? So, they in this paper they said we can use a gate. So, they have a gate. So, they multiply by g and this by 1 minus g, and this gate can be learned. So, they said you can learn it per head in that particular layer. So, per head you can learn this value as a sigmoid of Bg, right. So, Bg is a learned per head scalar parameter, right, and this can give you what is the value of g. So, and this can allow the heads to choose between whether they want to use more local or more long range attention. In the experiment, they found that most of the heads actually attended to the actional memory in that particular layer, right, and that helped them. But this is a mechanism that they have, so by which you can attend to both memory and the local context. Okay. So, to put them in picture, I mean this is what you have. So, you have a data store where what you are storing are keys and values for a very long context, right, for the current document. Now, given a query, you will attend to the local KV cache and also to this data store, right, and you have some gating mechanisms by which you can combine the output of both and get the final output, right, for this query. This is the KNN search augmented attention, but there are other ways you can do this. For example, this KNN language modeling is an idea where what they do is something slightly different. They say okay, so they say okay, during when you are doing inferencing, you will get a distribution, probability distribution, like you have a representation final HI, right, based on HI I can compute a distribution. Now, this hidden representation. Now, given this hidden representation, I can say I can search based on this representation, not through this query. So, the query is done over the KV cache, you get this distribution output and so on. You can compute a probability over all the tokens. They say okay, use this HI, not the QI, to find the k nearest neighbors from the data store, right. So, the data store will store again the representations for k items and the actual tokens. So, WIs are actual tokens, right. So, that is the difference. So, these are not key values, they are representations and the tokens. So, GI are the representations and WI are the tokens. So, you can use HI to actually put attention over all the GIs, right, the normal attention, general attention idea, and whichever you find the k nearest neighbors and take these top k words, right. So, you have some top k words. Now, they are actually words, right. Now, how do we use the words? So, say okay, we can use them to define a distribution over the entire vocabulary, because they are actual words. I can define a distribution over the entire vocabulary. How? So, you can say okay minus, so you can compute some output for each word. So, whatever you got from this GI times HI, you can use that to get an output for each word, that is 0 if the word was not looked up, and so distance between HI and GI if WJ is an entry in the vocabulary, otherwise 0. So, you can use that and create a softmax over vocabulary, right. So, it is a distribution again. So, you have a distribution from KNN, you have a distribution from HI, right. You can interpolate the distribution, right. So, here in the previous case you are interpolating at the self attention output level, here you are interpolating at the distribution level, right. So, you can do the KNN distribution and the LM distribution and interpolate. So, this is the KNN language modeling idea. And then you can go even to the next level, saying okay, what we can do, suppose I have an input context and my data store contains all the data. I do not even talk about my representation and the word, but I contains the data. So, I find the k nearest neighbor. So, actually context that are matching this actual data points that are matching this context, and I plug them directly as my additional context, right. So, I have this plus I am adding this additional context based on the similarity search, right, and this is famously known as a retrieval augmented generation, where I retrieve from data store and this retrieved information is added to my context, and this is what is used to give a message, is the prompt, and this is what is used to get an output from the LLM, right. Now, this we will spend one full lecture on retrieval augmented generation. That will be the final lecture in this week, that how do we use this external data through retrieval augmented generation, right. Okay, so, foundation of large language models will be a reference for this lecture as well, and along with all the papers that we talked about, and we will have one more lecture talking about RAG models for this week. Thank you.